Welcome to another CEO Wisdom Pod. We have Brian Feth with us. He's the Chief Executive Officer at Xcell Biosciences in the Bay Area. Brian is a life science entrepreneur. He's passionate about creating transformative changes in human health through powerful new technology and to better understand and destroy cancer, which is a fascinating mission. I don't often talk to entrepreneurs that have a very strong life mission. So it's always nice to get people like Brian on this podcast there. So back then he was in the corporate realm, I would guess, at Novartis and a bunch of biotech companies. But nowadays, since more than 15 years now, he's been the head of this beautiful company that is Xcell Biosciences. So eager to jump right in today. But before we do, this podcast presented by bookwritegpt.com. If you want to take your LinkedIn profile, convert them into a nice Kindle ebook, you can do so at bookwritegpt.com. Brian, welcome to the pod. Tell me a bit more about yourself and what you're up to nowadays.
Thanks, Charles. I'm the CEO and co-founder of Xcell Biosciences, which is a Berkeley ecosystem started company here in just locally in the Bay Area. We kind of started this company really around this idea that tool sets really did not exist to explore and understand cancer in ways that needed to be present. So most people had been focused on cell lines that have existed for decades and kind of used those as models for the disease. But we were moving into a world where we start to understand that every cancer is a little bit different. And so the company's early mission was really to just try to create a better tool set for understanding, growing, and interrogating patients' actual tumors. And I think, everybody's been touched by cancer in some way. I've lost 3 of my 4 grandparents to it. Both my parents have had battles with it. It's just ever present, and it feels like there's no one that hasn't had a friend or a family member that's been affected by it. And I think the really exciting thing and where our company has moved into and the existence and kind of reason to be that we have today is really focused on the evolution of cancer treatments. Most people, when they think about cancer treatments, they think about chemotherapy, which is a really blunt instrument. It destroys rapidly growing cells like hair follicles, taste buds, lining of the colon, and that creates a lot of really negative side effects. And in some ways, the medicine's worse than the treatment, than the benefit. It really has limited benefits, maybe knocking back the disease for a period of time, but is by no means a cure. And it has been the main tool set for decades now. And then radiation, which is kind of a similar approach to just trying to really mangle the DNA in the affected cells to get them to self-destruct, can come with a lot of side effects as well, a lot of toxicities. Over the last couple decades, maybe 20 or 30 years, there's been the advent of more targeted therapies that are kind of these specific proteins that bind to specific aspects of a tumor and can flag the immune system or kill the tumor directly itself. But those, you have to have a specific target in mind to really hit those cleanly. And sometimes there's off-target effects. Sometimes it's just a very narrow sliver of a population within cancer. So it's by no means a silver bullet. I think the really exciting part, which gives me, I'm very enthusiastic to share with people, is that there's been a huge amount of improvements in therapeutic potential over the last 10 years. And that's really been the recognition that the immune system plays a really important role in actually getting rid of cancer. And in fact, a lot of people get cancer and just never know it because the immune system does its job and gets rid of the cancerous cells before they actually can form a tumor mass and create problems. And it's only once that tumor kind of figures out how to cloak itself or, basically create an interaction with the immune system that blocks it from killing it, that you start to get cancers that go out of control and can really overgrow and metastasize. So this area of immune therapy has been a really important and really successful area. And so my company works on a specific kind of leading edge aspect of that, which is taking the immune cells out of a patient, using the modern day tools of genetic modification, which there have been some Nobel Prizes and a lot of advancements made recently in this area, and using those tools to turn these immune cells into heat-seeking missiles, where when you put them back in the body, they still do the normal thing. It's kind of They talk to other immune cells. There's a huge kind of variety of immune cells that have different roles in the body, and they can still engage in that. They can still go to the places like the thymus where they're they can communicate with other cells, but then they have this ability to also seek out and destroy or flag the tumor itself that people are after and alert the immune system. And in blood-based cancers, these therapies, usually 80 to 90% of patients, they see the disease just disappear within a 2 or 3 week period of time. And then about half the time it comes back. So curing about half the patients that have leukemias and lymphomas that are specifically indicated for these therapies. And this class, they're very safe because it's your own cells. They're moving earlier and earlier. So we anticipate that maybe this year we'll see a first-line approval for these therapies. So big market opportunity. And my company focuses on the technologies to make this stuff and try to make it at scale.
So the 50-50 thing, has it been researched? And also, what is the usual, it's not receding the term, right? But when someone gets cancer again, what's the normal rate with the normal treatments?
Yeah, so currently these therapies have been later line or last line because they're new and they're expensive. And it does require you to take the cells out of the patient, expand them externally, and then put them back in. So it's not just a pill. But in blood-based cancers, there's been a number of indications that have been approved. Multiple myeloma is one that recently received an earlier line approval. And these therapies, they're curing about half the patients. And there's a lot of success stories. There's patients now that have been alive for 12 plus years after their initial treatment. The original clinical trials were done 13, 14 years ago. So a lot of patients still alive from those clinical trials. So it's now being discussed as a cure, which is a different word than we usually use in cancer. But it's the challenge has been that because it's such a manual process, it's so expensive and time consuming, it's been very difficult to scale this. The one example, this multiple myeloma drug was produced by a company called Legend. They were producing about 3,500 doses a year as of last year. They got a second line approval, and suddenly their addressable population is like 100,000 patients. And so to be able to go from this small number to this big number of patients to treat is really difficult in a manual process. They basically have to just replicate that process 100,000 times. And it's very difficult it's just almost impossible to be able to do that. So
right. And what's the cost if I use like your treatment? What would be the end cost for the consumer?
Yeah, normally the cost of goods is different than the price. The cost of actually manufacturing this stuff is estimated. There's kind of a range, but somewhere in the 100,000 range
for one machine, right?
Well, no, this is for the cost of making the drug for one patient.
Okay, got it.
That includes the labor, the the clean rooms that they use for manufacturing, the food that they give the cells, the media, all of that together is combined around 100,000. And then the price to the patient is around $350, $450, 100,000. So the margins, obviously, these companies are trying to make some of that money back that they invested to get these drugs, but it's still not like a pill where it's like 99% margin every pill that you punch out. And so there is a fair amount of expense, and that's where our cells are focused. And a lot of the market is looking at how do we lower the costs of production? How do we shrink the time so that you can start treating a lot more patients? And so our technology is focused on automation, kind of this fully closed automated system that allows cells to be more potent, and so you can use less cells. And so we're shrinking that process down to just a few days. Normally it's like 2 weeks.
Got it. And again, the cost of Avatar is $100K.
No. We have 3 different products.
Right.
And those products are the Avatar Odyssey, the Avatar AI, and the Avatar Foundry. And depending on which ones, the smaller products are kind of research use only, and they can price in the range of 15,000 up to 55, depending on bundles and whether they're incorporated in a Foundry purchase. And then the Foundry itself, we're kind of at parity, actually at a discount to most of the instruments that are out in the market, and those instruments are in the 200,000 to 300,000 range. So we've tried to focus on making sure that the benefit from our technology is you can push a lot more patients through over the same amount of time. And so for us, the instrument isn't really the focus in terms of cost. Like, you could almost kind of flip the model where it's like a razor blade. You give them, the instrument, and then it's really per patient you're selling bags. So that's kind of a classic model in the research space, and that's kind of how the system is set up for us as well. So it's really around the bags, the very sterile bags that we allow fully closed for liquid handling for the patients.
And when was your first prototype deployed? Because you've been like 15 years at it. It's a very long marathon, right? So when was the first prototype developed? And I'm guessing the latest one was Avatar AI, right?
Actually, the most recent is the Avatar Foundry. That's the GMP larger scale system. The first system, the Avatar Odyssey, we developed in, I think 2016 was when the kind of first one rolled off the line, and that was immediately sold to Bayer Healthcare. And they bought a couple of them. Actually, before they were available, they were kind of the customer that was pulling the products through and out. And then we kind of moved quickly into a number of other accounts. We have quite a few instruments at J&J, and about 14 units there. We recently announced last week that we have a long-term relationship that started in 2017 with Bluebird Bio, which makes a sickle cell anemia gene therapy. And our systems have been used there since then, and they've continued to buy more as they've moved through the clinic and now into the market. So every patient that receives their drug Lyfgenia is first, it runs through a potency assay in our systems before it's released to the patient. So we've been doing this for a while, largely without a commercial team. Our company, when you're a small startup, we're about 20 people. Everybody's a salesperson, and so we structured the company to have that as a focus while we continue with product development and partnerships.
And who's in charge of product and R&D, and how do you get customer feedback to iterate on the next versions?
Yeah, we have I would call it a three-pronged structure. We have a CTO, Shannon Eaker, who came from Cytiva, which used to be GE Healthcare. They're one of the incumbents in this space. They came into the space early. They had technologies that were used for making proteins from cell lines. And so they kind of took that technology and shifted it to be able to be used for immune cells. It can do the job, but it's not really fit for purpose and kind of built for scale. And it's missing some elements like a small to large scale capability to expand. And so it's still manual in a lot of ways, but Shannon had a lot of it, been there for like 14 years and had a lot of information around the workflows, the different elements and the components, a lot of network and relationships. And so he's able to really stand up our beta program and kind of drive the requirements of the system from a customer use perspective. Our VP of engineering came from a group called Dark Horse Consulting, which has an expertise in quality and regulatory consulting, as well as product development. So he's been really able to guide the product development process. He's the VP of engineering. And so he's an expert product manager, is able to guide us through the regulatory and quality requirements, and has been driving the team and an external partner around product development. And then we have a product manager who manages all the relationships and makes sure that things are balanced and moving forward in time. And that's with Yelena Bronovetsky.
And the machine itself, is it built where you are in the Bay Area? Do you import pieces from China? Do you 3D print some of these pieces, or do they have to all be like medically approved?
Yeah, so really, we have CE marks on our Odyssey system and the AI system. The Foundry is built to be GMP, and that does require a much higher level of sterility and for manufacturing and the consumables as well. So for the Odyssey and the AI, we do the manufacturing assembly here in San Francisco in our offices. And then for the Foundry, we actually have a subsidiary based in Australia, Xcell Biosciences Australia. They're in Melbourne, and that group organizes all of the manufacturing. All of the design and engineering went through them, and then now the manufacturing is kind of going through that subsidiary as well. So
right. And is it true that big pharma tends to keep the discoveries for themselves and only commercialize it when it's when it has an ROI vs just deploying real cancer cures right now? Do you believe in all of that as an insider, or as soon as they have the cure, they put it to market?
Every corporate structure has a different requirement for return on investment, because it really depends on what level of infrastructure you have. So for a lot of companies that are really heavy on a commercial scale, tons of salespeople, lots of application scientists in the field, they are predominantly set up as commercial structures. And so for them to kind of invest in R&D to be able to support that commercial structure, they have to have $1 billion drug. And so those groups will often invest in a range. They'll do it either through partnerships or through internal investment. And if they determine that a drug has a peak sales of 500 million, they'll look to license that out because there's value there. They wouldn't sit on that. There's a return for them. They can't commercialize it because it doesn't meet their investment, their NPV, their net present value thresholds for investing in projects and further. But there's still monetary value they can gain by licensing that out. And so the pharma industry really works in a lot of ways through these kind of sometimes pretty complicated licensing structures. And so those can get licensed out to new companies. A lot of times investors will come in to look for those assets and then start companies around those. And then the idea is really to de-risk those assets. And a lot of times if you can de-risk them, and it becomes a monetary stream, there's maybe mid-tier biotechs or larger biotechs that aren't quite, the massive titans in this space that can pick it up. And so there's kind of a lot of churn. Small companies will often take a lead a certain distance, and then they end up moving over to another company that can support it maybe through the rest of the clinical development and has a smaller or more targeted sales force. So it's the targeted sales force that's the value. If you're selling to the large companies have sales force that can go to small, narrow niches of specialty doctors, but they also go to the primary care physicians, and that's just a huge amount. Whereas a smaller company, they can just focus on cardiologists, for instance, and they'll just pull in cardiology drugs, and that way, it's worth it to invest in those products.
And do you believe we're gonna eradicate cancer in the next 5 years?
I don't think it's 5 years, but we certainly have a pathway to do that now. I think the really exciting thing was when I started the company and just, as I was going through college in my early career, we continued to look at, there was no silver bullet. That was kind of the paradigm. Like, we're going to have to pick off each one of these subsegments of cancer one at a time. And thereby narrowing this pool of cancers that are not addressable. With the immune system now as a lead in this process, there's a bunch of different strategies on how to get these immune cells to be effective. And there's still a lot of work to do. We haven't talked about solid tumors, but solid tumors they're about 90% of cancers. There have been a couple of cell therapies approved for them, but they're more of a challenge. They require a more potent product, which is something we're also focused on. And but those therapies are just right at the beginning. Like I said, last year, the first 2 approvals for cell therapies for solid tumors. So I think over the next 20 years, we're going to see huge progress made against, that solid tumor population. And we'll probably see mostly blood-based cancers at being cured. And so I think we're right at the threshold of being able to kind of deploy these cell therapies at scale. But there's a lot of problems, a lot of infrastructure problems, which we're focused on to be able to get to that scale and be able to treat patients. We're supply limited right now. And then there's a lot of innovation still needed to be done.
Right. What about cell therapy for biohackers like me or ultra athletes like me? I saw that you had some of that on your website.
I know what you're talking about. So we often kind of use the metaphor for our process of a cyclist going into the mountains. So when a cyclist is training, they'll go into a higher altitude environment where there's less oxygen. That creates a stress on the body. It forces the body to compensate for a lower oxygen environment by producing more stem cells to produce more red blood cells, and therefore be able to get more oxygen to the muscles. And that's a coping mechanism that happens in high altitude, that when you come back down to a low altitude environment, you get the benefit of a lot more oxygen to your muscles, and they're much more, kind of competitive capability. And so this has become, a standard part of competitive cycling now, is to do that training. And so we do the same thing with our instruments. We actually kind of starve these cells of oxygen and allow them to shift metabolically. And once they shift metabolically into a way to produce energy without a lot of abundance of oxygen, they just become much more persistent killers. And so that's kind of our trick, is that we make these cells much better killers through kind of atmospheric stress and priming, metabolic priming. As far as your question on, can we use this as for biohackers? There are a lot of professional basketball players that are going to other countries to receive stem cell treatments for their knees and for various aspects of the joint where you start to get erosion. I think things are always better through a process that validates the safety and efficacy of something, because it's very easy to look at anecdotal evidence that something works. But if you do it in a broader population, just the data doesn't suggest that it actually is true. So, but it's a big world. And I think there's a lot of advances being made outside of our country and in our country. And where there's a population that's willing to try something at risk, there will be a country or, a place that's willing to serve that. So I do think you're going to just see that at the front edge of all of the cell therapies, and there will be benefits. It just won't be really well regulated.
What was your take on the Theranos failure? Did it affected your company? What lessons did you learn from that?
Theranos' failure?
Yeah.
Yeah, I mean, they were way over their skis in terms of what they were messaging about their capabilities. They just were straight up lying. They had developed an instrument that was close to delivering on the promise that they had been telling investors, but they had problems. And the issue is that they were dealing with, in partnerships, raising capital. They needed to show that they were delivering on all the promises they made. And they were afraid to tell people that the system wasn't working well and they needed more time to fix it. And so instead of telling people that, they went into a secrecy mode, and they just started using kind of behind the curtain the standard tools. And then on top of that, they were very sloppy as a CLIA lab. They just weren't abiding by the requirements, and they're giving erroneous data. I mean, it was a mess, and it hurt the space. And that is not how biotech companies normally operate, and they shouldn't. Those companies should get caught, and those stories should be told.
So how far can the Silicon Valley of move fast and break things be applied to a biotech company?
Yeah, I mean, data for sure is going to be one of the biggest aspects. Biology just has huge amounts of data. The genome is billion base pairs. There's not much understood about a lot of the DNA. We have now tools to really interrogate at high scale the RNA, which is kind of the intermediary recipe between the DNA and protein, and the tools to be able to evaluate proteins at scale are improving quite a lot too. So there's lots of kind of primary, secondary, and tertiary data that's going to all inform us more about how a disease works. And then just modeling in the body how all the pathways are integrated. And there's just, that complexity has been talked about for decades and just hasn't been available to be able to actually pull everything together. So I think there was I think it was Deep Cell at Google. They started characterizing the protein shape. There's basic rules on how proteins fold based on kind of hydrophilic versus hydrophobic and polarity. And it's very difficult to do that as a human, but the computers have been able to, AI has been able to knock that out. So now we have protein structures that are being validated, and that's accelerating science. So there's just way more now through the tools of AI to interrogate than we have the ability to actually kind of explore. And I think, again, there's probably another role for AI in helping us select what things we should actually be looking at in these complex, data sets. So that's for sure going to be where it's driving growth.
Last but not least, have you been affected by the tariffs, and what's next for you this year?
Yeah. The tariffs are, the environment has been tough for biotech over the last couple of years. There has been a challenge in getting exits for a lot of the investors that are investing in this space. There's been relatively few IPOs. There's been relatively few mergers and acquisitions. And as a result, a lot of investors in this space have pulled back. And so the companies that are really being funded are investor-started companies or very large rounds for very select kind of inside types of deals. And I think we were hopeful that with the election passed, that we would get a period of relative calm and a little bit more predictability, which is you've probably heard many times in the last few days that business doesn't deal well with uncertainty. And unfortunately, we've moved into much more uncertainty. So from that standpoint, it's a bit challenging. Investment markets are still very tight. And then on the sales side, we do manufacture products here, so there will be impacts from counter tariffs as we ship and sell out. And then for systems that are made in Australia, it does help to have multiple sites of manufacturing, but that's really by product class rather than a full product set. So we're gonna be hit with that over the next year for sure.
Thank you for being on, Brian. Where can people find out more about you?
Yeah, I'm on LinkedIn. You can certainly reach out to me and message me there. Brian Feth. I don't remember that. Maybe it's just Brian_Feth is the LinkedIn address. And then xcellbio.com is how you can reach us, xcellbio.com.